All right, so we can start. So we are discussing delays in MOSFETs and whatever else we find of importance while discussing delays, we'll spend some time there as well. All right, so last lecture we were looking at CMOS inverter as a simple device which allows us to discuss delay in MOSFETs, and we had said that the expression for delay for, let's say, high to low delay is a reasonable expression which is given by here, by this particular basically, as we have been saying, delay is charged by current. Delay is charged by current. Let me put charged by current. And so the idea was, what is the charge that I have to supply? And in this case, what we are talking about, there is a capacitor here, CT net capacitor at this particular node. So this capacitor has to be charged and discharged, and the delay basically comes about because of that. As you can see here, this is the charge that I have to supply in the numerator. All this is the charge here. All this is the charge Q, and then the current. Right. So we've been saying that delay in all these devices comes about because you have to supply or remove charge, and there is a finite amount of current which is available. There's a limited amount of current which is available for supplying the charge or removing the charge, and that's why the delay comes about, right? So this is the expression that we have for delay. Okay. So let's go forward and analyze this particular delay, in a little bit more detail. And so what we need, one of the things that you see in this particular expression, as we said, the drain current is a little bit easier to understand, which we all know, mu C oxide prime VGS minus VT square by 2. You know, all of you know this expression in saturation region. So that is straightforward. So let's try and understand a little bit on the capacitance that is there at this particular node here. All right, so for that we have to look at the transistor structure. So the transistor structure that we normally draw quickly on board and all that is here. You know, we put source, we put drain, oxide, gate and all that. And many times you show body contact, we show it here at the bottom, but body contacts are, typically they are at the top itself. The body contact that I'm showing here, contact to the body, is here itself, to the P plus here, which you will see in a short while, right? So this is rather than drawing a contact at the bottom, this is a more accurate picture of the transistor here. Now this is also a schematic, right? And it's a geometrical drawing. Everything is square, as you can see here. This is a more realistic picture of the MOSFET that is there here. These are also, as you will see later on as we go into the course, this is also a conventional, let me say, a planar MOSFET. MOSFET which has been there with us for a long time, a planar MOSFET. Planar means everything, source, drain and gate are roughly on the same plane. Okay, of course gate is a little bit above this thing, but nevertheless one can talk about a planar MOSFET with everything being in the same plane. And there, so what you can see here is, if you look at the differences between the two figures, of course, the N plus region that you see here is more, you will not, as you try to implant N plus, you don't get a rectangular kind of a profile. You get more complicated profile that you see here. The other one is, you see that there is a spacer layer here. There are spacers layer here, right? So this is the gate here, from here to here, and then there is a spacer layer that is there. We'll not go into it. These are needed for fabrication from processing point of view. It's also it's an insulator, So we call it spacer layer. It's an insulator only, silicon dioxide, or let's say in simple cases. And of course you have p-type, right? P-type semiconductor here, right? So this, so what is missing in the first drawing, in first schematic, is the more complicated kind of a n plus layer and the presence of the spacer layer. These are sort of missing in this particular schematic here. This may be a little bit also, you know, in some sense it's more realistic, but in other sense maybe this one. So it shows you both a n-type and a p-type transistor. So we are talking about a CMOS inverter, so it shows you both of them. So note that in this gray region that you see here is all silicon, right? Silicon. These are, of course, you can see here n plus here, and you see the gate here. In red, whenever you see red, is usually polysilicon. Red is polysilicon. Under the polysilicon is a very thin gate oxide, and the contacts typically are, you know, so you have an NMOS here. Sorry, NMOS here. And you have a PMOS here. This is the PMOS here, right? P-type. PMOS here. So also important thing to note here is that there is this concept of active area and the rest of the area. The active area is where the transistor is made, right? So this, as you can see here, active area. This is where your NMOS transistor is there. This is also the active area where the PMOS transistor is there. So note that the PMOS is made in so the substrate is p-type. So NMOS is directly made on the substrate itself. For PMOS, you have to create a n-well here, a region of n-type, and then within that region of n-type, now you make your p plus and all that here, p plus, and you make your transistor. Sorry. P plus here. You make your transistor. You see also a body contact here. Body contact is being made here. This is n plus. The body contact for the PMOS is directly made here also. Now, the other thing to keep in mind is outside the active area is all silicon dioxide. Note that this is all silicon dioxide. Outside the area is it's all covered with silicon dioxide. Okay. And there are different kinds of silicon dioxide deposited using different methods and all that is there here. So this is also silicon dioxide. And the first layer of metal is over here. This is called metal 1. First layer of metal. Right? So first layer of metal, if you want to connect, for example, if you were making a CMOS inverter, you would connect these two together. Right? So on top you would do all that here. Okay, so this is a more sort of you know, it gives you a better feel for the transistors that are there here. Okay, so these are important, as you will see when we try to look at capacitance here. So our goal is, because we want to understand delay, so capacitances are there. So look at this particular picture then, the capacitors that are there in a MOSFET, all possibilities are shown here. There is a gate to source. There's a gate to source capacitance, between gate to drain capacitance, drain to body here, source to body here. And you could also talk about between gate and body, so that also is shown here. Right, so all I mean, most of the capacitors are shown over here. So when you look at when you want to you know, calculate or estimate the capacitance, so this is a cross-sectional view, right? It's a cross-sectional view. Cross-sectional view of a MOSFET. If you take a slice of it, this is what you would find. This is a top view. So you know the N plus source that you see here is a note that outside is all oxide. Just as you can see, oxide here, everywhere outside is oxide, right? So these are all oxide here. This is the active area. All this is the active area, right? Active area within which the transistor is made. This is your source N plus, this is your drain N plus, and in red is shown polysilicon, and under the polysilicon which is used as a gate, you know, it's N plus poly, which serves as a kind of a conducting layer, and under the poly is your thin, very thin gate oxide. Right, so this is the picture that we have, a simplified picture again of how your MOSFET from the top will look like. Okay, so besides the channel length, there are other things. This is this is the length of the source that you can see here, and this is the width of the transistor itself, W, width of the transistor. Okay, note that the carriers would be flowing, electrons would be flowing like this, right? So that's the length, and this is the width of the transistor. All right, so so this picture also we need to keep in our mind here, the top view of the picture here. Okay, so all right, so let's estimate the capacitances. So as you can see here, there are 1, 2, 3, 4, 5 capacitors that are there in this particular schematic. So when you look at the 5 capacitors, so we are talking about the transistor, of course, could be in saturation, linear region, cutoff, and the values of the capacitors are different in different regions here. So what we are talking about, the most of the time, or this is the place where transistor spends a lot more time, at least when it is switching. So saturation region, let's look at it here. So CGS, I'm not going to derive any of these things, we'll just take it. CGS, gate to source capacitance, is 2/3 Cox prime, which we know Cox prime is capacitance per unit area, the permittivity of silicon dioxide divided by the thickness of the silicon dioxide. With silicon dioxide, we are talking about the gate. Note that there are multiple SiO2s, right? We are talking about gate oxide thickness. So this is C oxide is clear to us. W, width of the transistor we have discussed, length of the transistor. This is the component that comes about from the channel. There's a channel component. Between gate and source, note that between gate and source you have N plus and all that, but you also have the channel here, right? Charge in the channel. And note, just keep in mind that capacitance comes about because of change in charge with respect to voltage. So what when you're looking at CGS, what you're doing is you're changing gate to source voltage. And then you're looking at what are the charges that are changing. So when you change the gate to source voltage, you're going to change the channel charge. Obviously, if you increase the gate voltage, you increase the channel charge. If you decrease the gate voltage, you decrease the channel charge, right? So that's where this is nothing. This part is coming about all from the channel charge. And the 2/3 comes about because it's not a simple parallel plate capacitor, right? So normal, you have gate, you have this thing, and you have the other thing, and then you say there's a fixed D, and so you write C equal to epsilon by D. So you say capacitance is epsilon by D. So this is not, it's like a parallel plate, but note that in saturation region, as you know, there's a lot of charge density close to the source, and then as you go towards the drain, the charge density decreases, and in pinch off it becomes almost very close to 0. So there's a non-uniform charge density. And because of non-uniform charge density is where this factor 2/3 comes about. If it were uniform, for example, let's say if you look at linear region, you know that transistor characteristics IDS versus VDS for a typical VGS will look like this, right? Will look like this. Suppose you're here, right at this, very close to this region here. very close to origin, right? You're in the linear region. You apply a VDS, let's say VDS of 10 millivolt. So then what you would find is channel charge is uniform. It's uniform channel charge. What do you think should be CGS? Channel charge is uniform. Your guess? So it looks like a parallel plate, right? In parallel plate is what? You have plus here, and your minus here, minus here. Uniform channel, uniform charge density everywhere. So your guess? CGS? CGS, so what you're saying is, if it's exactly like a parallel plate, so you will say Cox prime W times L, right? Except that, note that there are two terminals. There's this terminal and there is this terminal, both. And when drain voltage is very small, then drain and source are equivalent. So if I were to apply, let's say a sinusoid like this, suppose I apply a positive sinusoid. So if it's a positive sinusoid, you are increasing the charge on the gate, right? So now, which means that the charge has to flow out. You need more positive charge, right? At the gate, charge has to flow out. So it will flow out from here and it will flow out from here also. Both, there are two paths to it, and it will go to the gate, right? So it will flow through both terminals are equivalent when the drain voltage is small. And so therefore, what happens is between gate to source, you get half. Half the charge goes out from the source terminal, and half the charge goes out from the drain terminal. So the channel charge now divides between the two. If you increase the gate voltage, channel charge has to increase. It comes in, half comes in from source, half comes in from drain. If you reduce the gate voltage, channel charge has to come out, half will come out from the source, half will come out from the drain. So effectively capacitance becomes half between a particular set of pair terminals. So note that what is happening is, in saturation it is 2/3. Again, I'm not going into slightly more complicated. Maybe you'll do it in 614 or other courses. When you go into this is easier to understand. It's like a parallel plate capacitor, but with two terminals. Bottom, there are two terminals from which it comes out. It's almost like a picture like this here. So top plate is let's say gate, bottom plate is, let's say, half is source and the other half is drain. So now obviously capacitance will become half of the two, right? So you could think of half the charge. It's like a parallel plate, but the plate is split into two. And one plate is half the length, the other one is the half of the length. So it becomes half. Right? So this becomes in the linear region. So note the complication that occurs. The capacitance in saturation is different, capacitance in linear is different, and then capacitance in cutoff, we'll see in a minute, cutoff will also be different. Right, so these are coming about from the channel part here, channel region. And this one, it comes about because this diagram doesn't show it. There is an overlap, or it does show, if you can see here, there is a overlap in this tiny region here. There's an overlap between gate and source, right? So there's an overlap region here, and so that gives rise to, this is called overlap capacitance. And note that overlap capacitance is, there's a tiny overlap between the two. So we don't, normally you say capacitance is so many farads per centimeter square. Overlap capacitance is specified in farads per centimeter. It's like an edge capacitance. It's not an area. So it's on the edge that is there here. So it's specified as 4 farad by centimeter, and then depends on how much is the width of the transistor. So if this picture will show you more. That's where I said, where is the overlap capacitance? Is along this length here, this edge here. There's an overlap between them. And so it depends on how much is the width. The larger the width, the more the overlap capacitance here. And so there is an overlap capacitance here, and there's an overlap capacitance on this side also. Both sides there is an overlap capacitance between gate and source, and gate and drain, right? So you have to understand the source of these overlap capacitance here. Okay, so that is now, okay, so let me remove this part here. All right, so this will complicate. Okay, in saturation region, note that what is happening in, these are simple models, by the way. These are all simple models that is there. So two components, one is from the channel and the other is from the overlap, right? So we distinctly understand both of them. The gate to drain capacitance is only, first order approximation is only the overlap capacitance. Because note that once the, you know, if you look at this picture here, again, ID versus VD, right? You are here somewhere. As you change the drain voltage, the current is not changing, right? Why is the current not changing? Or why is the current changing here? What do you think is the reason for current changing? Here, as you change the drain voltage, current changes. While as you change the current voltage, it doesn't change here. What is happening? In the two regions, what is the basic difference? ID is changing a lot here, right? ID is changing a lot. ID is not changing much. First order, almost like, let's say, flat first order. Of course, it's not flat, but, right? So what is the basic difference? Why? Huh? No, we know saturation, but in one region, current is not changing with drain voltage. In other region, current is changing with drain voltage. So what is the reason? Why is the current changing here? Why did it become? Why is the current changing here in this region? So you're applying a voltage to the drain. So what is happening? Note that current is increasing, right? So if I increase delta VDS, then the current increases by a certain amount, right? It increases by a certain amount. So what is happening? Why is the current? So what is the, so if you were to draw a causal diagram, right? Draw a causal diagram of this, right? So we are looking at change in IDS. And we have VDS. Okay, so how does VDS cause a change in IDS? Change in channel charge. Okay, so one factor that you're saying is, let me write channel charge, QCH. So if I increase VDS, what does it do to the channel charge? What does it do to the channel charge? Should I put a plus here or minus here? Should I put a plus or a minus? Increase in VDS, will it cause channel charge to increase or decrease? Plus or minus? Minus? Because note that channel charges, you think about it like a parallel plate. One plate is on top and the other plate is this. If you increase the voltage of the bottom plate, what will happen? Charge will decrease, right? So minus. What should I put between here and here? Increase in channel charge will cause increase in current. So that's okay. This causal diagram of VDS, increase in VDS will cause decrease in channel charge, will cause. So increase in VDS is causing what? Increase in VDS appears to be causing a decrease in current, because increase, note that VDS increase will cause channel charge to decrease, will cause drain to source current to decrease. So what is the other factor? Huh? Drift velocity. So yes, so VDS increase, if you would like, is causing an increase in electric field, right? In the channel. So you'll say plus. And electric field is causing, as he says, drift velocity. plus drift velocity of electrons, and this is causing a plus higher current, drift current. Correct? So now you have another path. So why is so if you look at this path, this path increase in VDS is causing a increase in VDS, while this path is causing a reduction in current. So why does the current increase then? Why does the current increase? Is it because this has more effect, more dominant as compared to this one here. There are this is what is happening as you change the drain to source voltage. There's an upper path, effect on the current, and then there's a lower effect on the current. So now when you enter into saturation, what do you think happens? As you said, so this dominates here, right? This path dominates and you start getting an increase in current. Fine. But if I go into saturation region, this, let's say in linear region. Oops. If I go into saturation region, what do you think will happen? You are saying in saturation region sort of pinch off occurs, right? Now what do you think? As I change drain to source voltage, does channel charge change? What is happening? If channel charge will change, then VDS will change. So what happens is the moment you create a pinch off, note that when you are here, drain when it's flat, what is happening is drain is losing control over the current. Drain has no control over the current. So what is happening is the moment you create a pinch off here, what else can you do to that particular point? If it's already pinched off, that means you can keep on reducing the channel charge, but eventually if something becomes zero, that's it. You can't make it negative, right? You can't go negative. So what happens is this path is no longer active. There is no pinch off has occurred. Charge next to the drain has gone to zero. So a drain is no longer able to affect the channel charge. First order, I'm saying. Okay. Of course, those who know there's a channel and modulation, it little bit shrinks and all that. But first order, drain is not able to affect the channel charge. And not only that, if you do an analysis, you find that the voltage next to, there's a pinch off point, as you know, the voltage at this point is VD sat, it remains there. So it's not able to affect the electric field also. So neither can it affect the channel charge, nor it can affect the electric field. And therefore the current becomes constant. So it loses control over both channel charge also and the electric field within the channel also. And the current then becomes constant. But note, if you are losing control over the channel charge, then what does it imply about capacitance resulting from channel charge? Zero. If a change in drain to source voltage cannot change the channel charge, which means capacitance is zero. That's why we have not put anything here. This component is not there. You see, this component which comes because of channel is not there in this part here. There is no channel component here. But overlap capacitance is there. Right? So this is what what is happening as you go towards the saturation region. Anyway, so I would again suggest, although these are simple things, get into the habit of drawing these causal diagrams. It would help you. Wherever you are and you want to understand the mechanism, draw your own causal diagram. What is my primary variable? What is my secondary variable? Sketch out these. It would help you to understand that particular topic or mechanism a little bit better. All right, so we know now that gate to drain capacitance has only the overlap capacitance part, gate to source has both. And now let's come to, when we discuss capacitors in these MOSFETs, there is an important point to remember. So we are coming to gate to source and gate to drain we know now. Now the other ones are source to body and drain to body. Both of them are of similar nature. Both are N plus P PN junction capacitances. Both are like reverse bias capacitances here. But in the discussion, what you need to remember is the following. The capacitors have normally, you know, when we write capacitor, we say epsilon by D into area. Right? We just write like that. But capacitances always have two components. There's an area component and there's a perimeter component. Right? So if you look at this one here, if you look at a parallel plate capacitor, this is the top plate and this is the bottom plate. You have field lines which are, you know, you see all this. Right? The normal field lines which are there. But then there are these fringe outside, just at the fringe. These are this fringe electric field. Here. So there is a capacitance which comes about because of the normal field that you are familiar with, and there's a capacitance that comes about because of these fringe fields that go through the, you know, the surrounding media that is there here. Right, so when you write C equal to epsilon by D area, is only referring to this part here, from here to here. It's just referring to that. It's based on field lines which go, you know, epsilon by D and all that comes about from that also. But note that there is this, if you have positive charge here and negative charge here, it's going to go like this also. It's going to go like this also. So fringe is also there. Right? So that also. So if I'm showing you here as parallel plate, this is one metal plate, M1, and behind is the other metal plate, M2. And in between is the dielectric, let's say SiO2. So if I look at the net capacitance between the two plates, there is this standard capacitance that you're familiar with, epsilon by D, W into L. But then there is a fringe capacitance that comes about, and the fringe is only related to perimeter, because fringe is not the area component. Fringe is all along the sides, you know, because of the field here, because of the field here, the field here, the field here, here, right? The field here. Let's say this is positive plate here, so the positive plate here, there's a negative charge here on the other side here, so the fringe capacitance is all here, and then you can't see on the other side and all that. So the fringe is all along the fringe, as the word indicates, all along the fringe, all along the boundary. So this depends on the perimeter, twice of W and twice of L, and we call as the perimeter capacitance here, whatever is that fringe capacitance. You can calculate, calculations are a bit difficult because it's a two-dimensional phenomena, or you can measure it. Right, so there are always these two capacitors that are there. Now the thing is, when you know, if I were to calculate this, and if I have a large plate, you know, the plate is, let's say 1 millimeter by 1 millimeter, right? What you would find is this area dominance, area part dominance, and perimeter part is very, very small, right? But then, in fact, if you can yourself see here, if you take the ratio of the two components, this is the area component and this is the perimeter component. Let's call this C1 and C2. And let's say C1 by C2. Right, so C1 by C2 will go as proportional to W into L by, let's take it out, L plus W. So let's say W and L are similar. So you get L square and you get L, and this is proportional to L. Right, C1 by C2 is proportional to, roughly proportional to the size of the plate that is there here. C1 by C2. So note that if L is large, then C1 by C2 is fairly large. But as L becomes small, the importance of C2 increases. As L becomes small, the importance of C2 increases. And in fact, surprisingly for you, you will reach a threshold where C2 becomes larger than C1 if you go to sufficiently small L. C2 becomes larger than C1. The fringe capacitances are much higher than the area part here. And now when you go to smaller L means what? That's the place where you're going, VLSI, right? You're going to a smaller and smaller transistors, smaller and smaller sizes. So in those, what you find is, in many of the calculations that if you do, you'll find the fringe capacitance is much higher than the area part here. right? So it's extremely important for you. Normally we say epsilon by d, and we forget about it. But the moment you go into these realms, some microns and all that, the fringe part is very, very important. You can't neglect it. So every capacitance that you look at, you should look at it, all capacitors that you should look at, you should always ask, what is the area component, what is the perimeter component, right? And in a way, we've already done that, right? If you look at it, for example, when I wrote CGS, we said what is the area component and what is the perimeter component. We've already seen here. We've already taken into account a perimeter component. This is like W here, okay? So everywhere that you need to keep in mind is that you need to take into account the area and the perimeter component. Okay, so with that background, so if I look at source to body and drain to body, these capacitors will have two components. Note that source to body, right? So if I write source to body and drain to body is the same. So look at the source to body that I'm writing, CJ. CJ is what? Junction capacitance. Junction is, we have a PN junction. Junction capacitance, so this part is a standard PN junction formula for capacitance. Standard formula. This is how capacitance of a PN junction goes. Reverse bias capacitance. And this is the area of the source. Area of the source would be, as you can see here, W times Ls. W here and L here. Total area of the source. Right? And if you're wondering, this is the source to body voltage, this is the built-in voltage PB, some different maybe terminology is used. This is the built-in voltage of the junction. This is the zero bias capacitance. When you don't apply any source to body voltage, equilibrium capacitance. And MJ, normally this may be half, but it depends on the nature of the, it's not an abrupt junction, it's the doping profiles are more complicated, so it's not really half, it's some other value. So it's a general expression for PN junction, PN junction, zero bias or reverse bias capacitors, and depends on the area. So this part is clear. Now there is another part that is, as I've said, this comes from the perimeter. So the perimeter part is also like a PN junction part, but we are talking about capacitance here, along this periphery, and along this periphery. And therefore it is 2 times Ls and plus W. 1 W and 1 Ls and 1 Ls here. If you're wondering why am I taking on this side, because this capacitance, overlap capacitance, has already been put in CGS. We don't need to take that into account. Okay, so there is a perimeter part that is there. So same thing is with the drain to body. So there is a grading coefficient and all those things are there. Similarly, drain to body capacitance here. Okay. Now, if you're wondering, okay, so the last component, so we have already talked about CGS, C gate to drain, C source to body, C drain to body. If you're talking about between gate to body, what about between, there is a gate here and there is body here. What about the capacitance here? So this capacitance is, gate to body capacitance is, there is only a overlap part which is there here, because note that once you are in the strong inversion condition, if you change the gate voltage here, you don't change the depletion charge. As you know, once inversion layer forms, depletion capacitance doesn't change. So which means that if you are going to increase the gate voltage, the depletion charge that is there in the body, it doesn't change. First order. Okay, it doesn't change, and so therefore there is no communication between the gate and the body. You change gate voltage, nothing changes in the body. Once you are under strong inversion, nothing changes in the body. The only thing that is left is an overlap capacitance along the fringe here, along this side and this side here. So there is no area component because no field lines are penetrating. Once the inversion layer forms, the inversion layer acts as a shield. It doesn't allow any field lines to go through. Right? So note that you have N plus, and before you form the inversion layer, you have the depletion width. And there's an electric field lines of your positive charge here, and the positive charge terminates over negative in the depletion region and all that. But once you form a inversion layer here, then your charges are all at the surface, and any change in the gate will only cause a change in the charge in the surface inversion layer. So nothing really happens at this particular point. In the bulk no longer responds to the change in the gate voltage here. So that's where there is no area component of the capacitance. So you're left with some fringe lines here and here between the body and all that. So this is where you have only this particular capacitance here. So often a negligible part of the capacitance, gate to body, is the smallest component, and many times in the simple analysis we often just neglect it altogether. Okay, so we have all the capacitors and potentially we can calculate all of them if we have all the dimensions here. So this is the final, if you want to look at a small signal model. Small signal model is over here. All the I hope you can recognize all the elements that are there. So there is gate, obviously there is drain, and there is source, and there is body. And we are talking about a transistor where the source is grounded, body is also grounded, gate is here, and drain is connected to a constant voltage here, VDD or something. All right, we are talking about that situation. And so for that is what we are drawing. So under small signal condition, drain is small signal ground, source is also ground, body is also ground, and the gate is given here. Now between gate and source, you see the capacitance CGS that we have drawn. Between gate and drain, we have drawn the capacitance CGD. Between drain and body, we have drawn the capacitance CDB. Between source and body, we have drawn the capacitance source to body capacitance, which you have seen. Between gate and body, we have drawn CGB. So all the capacitors we have drawn, right? So all the 5 capacitors that you see here are all there. And the usual, voltage control current source, GM, VGS. And this is not there because body and source are both grounded, so this term is not there. GM, from the body side, if there is any change in body to source voltage, that can also cause a small signal change here. So this is not there here. All right, so for this case here, so we are talking about this situation here, okay? So this small signal model then simplifies to what you see over here, right? Because note that source to body capacitors gets shorted out, so we have eliminated that. There is no, this part is not there, right? And R0 also, source to drain gets shorted out. This is also gone, right? So we end up with this simplified small signal model, where we have kept all the capacitance CGB, CGS, CGD here. Now what we are doing is we are trying to find out the UGF here, unity gain frequency. And so in unity gain frequency, what we are doing is we are adding a sinusoidal current here. sinusoidal current here, and we are looking at sinusoidal current in the drain, right? Or what you do is you put here maybe a VGS and look at the current here, IG. And so what you're doing is defining a gain, beta, which is ID by IG. The ratio of drain current to ratio of gate current, small signal current, AC current, small signal current, right? And then you look at how beta changes with frequency. And the place where beta goes to 1 is the one which we call as the unity gain frequency. So that's the reason why we are trying to calculate what is the gate current. So gate current will come about because, as you can see here, there are 3 contributions to the gate current. Gate current can flow here, gate current can flow here, and gate current can flow here. 3 components, and both are capacitive components. So that's where you have j omega, CGS, CGD, C gate to times VG. So that's the gate current. And the drain current, well, drain current, you can see 2 components. One is going here, and the other one is going here. Possibility of drain current being, flowing from here. This component is much smaller than the this component most of the time. So that's where we have written ID equal to simply GM/VGS. And then you take the ratio of the 2, ID by IG, so you get beta. And then you find out when does this current gain go to 1. Well, the current gain will go to 1 when this ratio is equal to 1, GM by omega T equal to 1. So that's we are calling as the unity gain frequency. So we get omega T equal to omega is GM by CGS plus CGD plus CGB. And so finally we get this omega T is nothing but 2 pi FT. Now I've already shown you that gate to body capacitance is negligible in saturation region, and gate to drain capacitance has only the overlap part, doesn't have the channel part. So this is also first order. Maybe it can be as much as 1/10 of the CGS capacitor here. So that's where, to get a simple expression for FT, we have kept only the first part of the capacitor. So FT becomes GM by 2 pi CGS. And if we plug in the expression for GM, and CGS have already given you, and we keep in CGS only the channel part, we ignore the overlap part, then we get FT equal to this one here. So this is the highest speed at which a MOSFET can, highest frequency up to which a MOSFET could potentially operate. I'm not saying it will, but beyond FT, a MOSFET is practically useless. Where note that what does FT imply? That the gate current, sinusoidal gate current, is the same magnitude as the sinusoidal drain current, right? So it's practically useless beyond FT. Below FT, it may be of some value, of some use, right? So you could use it. So it's the highest frequency at which the MOSFET could be considered as a useful device, right? So this is the an important expression which tells you the upper limit on speed of a MOSFET here, unity gain frequency of the MOSFET here. So just like for bipolar we were studying, similarly now these are all based on long channel theory. Assuming the MOSFET is fairly long, no short channel effects and all that are taking care. So it's a long channel theory based. So of course this expression is important because it tells us, despite its limitations, it tells us several things that are important. One is obviously way to make the MOSFET faster is L. Scale the channel length. Reduce the channel length and the MOSFET will become a faster MOSFET. The other one is mobility. Silicon has, it's not a high mobility device. If you could make MOSFETs on indium gallium arsenide, and there are other materials as well, which give you better mobility, well, then you'll get a faster MOSFET. Mobility obviously is important. The other one is the voltage at which you operate, which we saw in the last thing also. The higher the voltage at which you operate, you are able to operate, the higher the FT is, unity gain frequency. Okay. All right. So this sort of captures some of the important things that are there in terms of delay or speed of a MOSFET here. Inversely proportional channel length, mobility, and the operating voltage. All right. So this I'll skip. If you're so this is a small signal delay, right? Small signal delay of a MOSFET, where we are talking about small signal analysis here. If you are interested in a large signal delay, a very simple large signal delay, tau equal to Q times, let's say, I would suggest that what you do is you write Q as simply we have CGS, very simple expression. CGS is here, so you could do CGS times, let's say, VDD is your charge, and you have I, which is W by L mu Cox prime. Maybe just write VGS, or you could do VDD, or let's take accurate. VGS minus VT square by 2. Divide the two, get an expression for tau, and you will see similar thing here. Do that by yourself, you'll see same factors. Mobility, L square, VGS, exactly same factors that are there here, even here. Right? So do this by yourself and check this large signal delay if you want. This much charge I have to supply, this much current is available. Okay, now more realistic, if you want expressions for delay, then these are okay to, they capture the factors qualitatively. If you want more accurate description of delay, then you have to go towards in CMOS inverter. And then you need to talk about, as we were trying to do in the last lecture, by looking at expressions like this, and then looking at then all the capacitors properly, accounting for all the capacitors that are there at this particular node here. If you're looking at, for example, delay due to inverter like this, put a load also, and then start calculating all the capacitors. So let me see if just to give you an idea. All right, so look at the total capacitors at this particular point here. So in this case, what I'm doing, I'm taking the input, and from input I've gone from VDD to 0. If I go from VDD to 0, immediately this transistor goes into cutoff, and this transistor turns on, right? It turns on, but it starts in saturation and eventually goes to linear. That's what will happen. If you just, initially this one is at 0, and the transistor is starting from saturation to linear. So note that you have to look at the capacitors of this. If I look at the total capacitor at this particular node, at this node, I have to talk about capacitor due to M1, capacitor due to M2, capacitor due to M3, capacitors due to M4. This is a realistic situation because one inverter is driving another inverter. So you have to look at M1, M2, M3, M4. The complication is, okay, so this goes into cutoff. So I have to use capacitors which are appropriate for cutoff condition. This one starts from saturation, then goes to linear. Capacitors are different under saturation and linear. This one, look at what is happening during transition. This one is starting from, initially this is 0. Right? So this one starts from cutoff, but then as it charges, it goes into saturation and then goes into linear. This one starts off from linear, then goes into cutoff. Right? So the transistors are also making a transition from linear, cutoff, saturation and all that, and capacitors are different in different regions. Right? So this makes the whole thing sort of complicated. Exact analysis becomes complicated, so you start ending up and calculating what is the average capacitance. So note that this is where I've shown you all the capacitors that are there here. The first set of capacitors are, we are talking about delay of the first inverter, inverter number 1. These in black is the capacitance of the inverter 1, intrinsic capacitance. and in red are all the capacitors of the load. All the capacitors of the load. These are what? Gate to source, gate to drain, gate to body, gate to source of the PMOS, gate to drain of this thing, gate to body. These are all the gate to source, gate to body, all these capacitors that are there. So you have to sum them up and you have to calculate, right? So you have to do all of that. So that's the first complication. Looking at all the capacitors that are there, calculating the numbers, and taking appropriate values, cutoff, linear, saturation, all that is there here. Okay, let me come to this one. Okay. Now to calculate, note that now the difficulty that comes in is the following. If you try to look at the expression for gate to drain capacitance, we had written gate to drain capacitance as overlap some capacitance, C overlap multiplied by W. Or if we look at gate to source capacitance, CGS, we had written 2/3 C oxide prime W times L plus CGS0 times W. Right? We had written all of that. Now note that how does the design proceed? You design, you have some specifications, and then you go ahead and do a design, and then you end up with a schematic like this. Right? And in a schematic, what do you have? The structure, and you have information about W by L. The size. You have the information about W by L. Like this inverter could be, you may say this inverter is, let's say 2 micron by 0.5 micron or whatever. And this is 1 micron by 0.5 micron, something like that, let's say. So once you're done with the design, initial part of the design, you have a schematic with you. And in schematic, you have the sizes with you. So with the size, you can estimate CGSN and CGDN and all that. But how do you estimate drain to body? Go back and see. Drain to body capacitance requires what? Requires what? Drain to body capacitance? Area of the drain and perimeter of the drain. Where is this information in the schematic? Two micron and 1 micron. Where is the information about area of the drain and perimeter of the drain? There's no information about area of the drain and perimeter of the drain. When you are done with schematic design, all you have is W by L. You don't have area of the drain and perimeter of the drain. So the issue is, how do I estimate this then? How do I estimate this? How do I estimate here? How do I get these values without knowing the area of the drain and perimeter of the drain? Where will these things come from? Well, you have to do the layout, because these are geometrical information. So you have to do the layout, which means that you have to take this schematic and convert it into a layout like this. So all of you are doing 610? Any layout so far? Layout you've been doing? No? Not yet? So probably it will be coming in the second half. Okay? Probably layouts and all that will be coming in the second half. But this is showing you the, what do I mean by layout? Layout is the transistor has a certain size, it is placed somewhere at certain point. Right? So note that in this, what I have is, let me draw the this thing here. This is, obviously everybody is familiar with, right? Now I have drawn this in a certain units called lambda, 4 lambda by 2 lambda, and I've written 8 lambda by 2 lambda. Lambda is a very simple way of taking into account which technology are you working with. If I'm working with 1 micron technology, lambda is approximately 0.5 micron. If I'm working with 0.5 micron technology, lambda is 0.25. If I'm working with 180 nanometer technology, lambda is approximately 90 nanometer. Right? So it's a, when I express everything in terms of lambda, then it's like like an abstract representation. Any technology that you want, I can go to that particular technology by simply changing the value of lambda. Okay, so it's a more general way of talking about a layout here. So that's where I've written everything in terms of lambda here. The units are lambda. Lambda could change. Okay, lambda could change depending on the technology. So note that this is your inverter. So this is where the layout, this is where the transistor is, NMOS. This is where the NMOS transistor is drawn, NMOS, and this is where is this NMOS, and this is where is the PMOS, and this is where is the drain of the PMOS, DP, and this is the drain of the NMOS, DN, and they're being connected by a metal, and you're taking output. It's a line of, it's a you know, lines are no longer a line, but it has a certain width and all that, right? So this is the this part there. So you know, so you have to do a layout, and in layout, note that what we are doing is, this is the if you look at, so I will not go into the details of this. So this is where this whole thing that you see here is this part, is this your source, is this source here, is this whole thing is source. This part starting from here and here is your drain. That whole thing is your drain of the transistor, drain and source. So if you're saying, why am I making like this? Because note that I have to make a contact to the source also. I have to make a contact to the source. So that's where this is the contact that is being made to the source here, and contact which is being made to the drain here. This part is the gate here. In red is where you're seeing the gate here. Right, so this is how the transistor will be, the NMOS that you're seeing here, the transistor will be fabricated. This transistor that you're seeing here will be fabricated. This length is 2 lambda, and this length from here to here is 4 lambda. So this is where the transistor is. If you're thinking about the gate area, this is the gate area. Right, so this is that you're seeing is your NMOS transistor. Now, when I say I need the drain area, so drain is this part here, entire from here, 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 here. This is the drain here. If I can draw here, all this area is the drain. And all this area is the source. This whole thing is source. So I need the area of these. And along the periphery, if I go here, along the perimeter is where I will get the perimeter of the drain. And similarly, perimeter of the source. I have to go towards the perimeter of this part here, 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 and here. Then only I will get the perimeter part here. The boundary of the source, the boundary of the drain will give me the perimeter part. So the point that I'm saying is, you have to go towards and do the layout. You have to do the layout, and only then you will get the source area and the drain area. And then only you can compute. Then only you can compute the capacitance. Then only you need these things to compute a very important capacitance, which is drain to body. Drain to body capacitor at this particular point, capacitor is at this node, and drain to body capacitor cannot be estimated, or source to body capacitor if it's required, cannot be estimated unless you know the area of the source and area of the drain. So one of the very common mistakes that people do is, you know, they take a schematic and then they start simulating it, right? And they start simulating it, and simulator has no information about, let's say, area drain and perimeter drain. So it doesn't have any, it will just put the value of the capacitor as 0, or will take some default value which are wrong. And so you'll get all wrong results for your delay, for your unity gain frequency, everything will be wrong because you don't have proper area of the drain and proper perimeter of the drain if you don't feed it into the simulator. All your delay calculations, everything will be wrong without this particular, and I will show you some sample calculation, is one of the most important capacitors that are there, drain to body capacitor. Right, so without doing, now what people will tend to do is, I have not done the layout, but they will use some formula for an area of the drain or perimeter of the drain and try to predict. You can try to predict without doing the layout. Well, this is likely to be area of the drain, this is likely to be perimeter of the drain, fine. You can do that to estimate a value of this thing here. But it's very important that this information is available to you. In some form, this information is required to calculate the values of the capacitors that are there. All right, so let me, I'll show you some sample calculations. You can see from this, this thing here. So these are the capacitors that are there, at net capacitor at this particular node that I've done for a sample, let's say 0.5 micron technology, to give you an idea of relative magnitudes. Right, so look at the, so the first set of capacitances are coming from the inverter itself, intrinsic capacitance. So drain, gate to drain 0.3 femtofarad, drain to body 6 femtofarad. This coming from the NMOS. This is coming from the PMOS, 0.6 femtofarad, 6 femtofarad. Right, these are intrinsic capacitances. Right, so at this particular node, due to the inverter itself. All right, and this is coming from, the second ones are coming from the load, from the NMOS load, gate to source drain and gate to drain 2 femtofarad, and gate to source drain and gate to drain 5 femtofarad. So just look at the numbers here. If you look at a single component, which component stands out for you? Which is the highest value? Huh? Drain to body. The most important capacitance in all the, if one single term which has the highest value, drain to body. It's not gate to source, it's not gate to drain. Gate to drain is smaller, drain to body. Very important. I'm not minimizing this. This is also very important. Gate to source is very important here, that you can see here. These are also, but drain to body capacitance that you can see is so important here. So important here. And that requires your area of the drain and perimeter of the drain. Without that, you cannot calculate. So this is giving you the relative magnitudes of all the, so note that this is where, for example, when I calculated a very simple expression for delay, I said tau equal to Q by I. Right, and said Q is CGS times VDD by I. So I'm only looking at delay in terms of only CGS. But then when I go to an inverter, what do I see? Look at, if I go to an inverter and I see total capacitance is what? All this term here. And CGS is a 2 femtofarad, it's not the only capacitors that are there. There are a huge number of other capacitors. So that's where the delay that you get from these simple expressions or UGF is like the upper limit. You will never be able to, in a practical cases, reach that. Other capacitors also come into picture. You'll not be able to go towards UGF. You'll not be able to operate the transistor at UGF, at that higher frequency, because all the other capacitors are also there. UGF is a very, you're talking about UGF as, you're taking a transistor, this is ground, and drain is connected to VDD, fixed drain. It's a very artificial situation. You're not going to get drain connected to VDD. Drain will be connected to some load, some other things and all that. This is not going to happen here. Right? So it's a very artificial situation. It's like an upper limit, unity gain frequency, but maybe appropriate name would be upper limit of frequency or something like that. U should stand for upper rather than maybe unity. Okay. All right. So let me stop here.